Welcome to the fourth lesson of fourth module, which is on torsion part 4. Now, in the previous 3 lessons on torsion, we have seen several aspects that what happens to a bar when it is subjected to a twisting moment, and this twisting moment could be in a bar which is of solid circular shaft, or could be in a bar which is having a cross section which is tubular in form. That means, there is hollowness in the shaft. And also we have seen if these bars are used for transmitting mechanical power to some other devices, then how the stresses and the deformation generate. Now, we are going to look into some more aspect of torsion in this particular lesson. Now, it is expected that once this particular lesson is completed, one should be able to understand the concept of tensile stress and failure pattern due to torsion. In fact, we will look into that due to the twisting moment. We have seen that the shear stress generate, and we have the maximum stress on the periphery or the surface of the bar, and then we look into that what are the values of the maximum normal stresses and what is the consequence of those normal stresses in the bar. Secondly, we will look into that one should be able to understand the effect of torsion in indeterminate system. Now, so long we have discussed aspects of the determinate system. That means, if the twisting moment is acting in a bar, then we can evaluate the resisting twisting moment from simple equilibrium equations. Now, we are going to look into the systems where by using equilibrium equations alone the internal resisting twisting moment cannot be determined. So, as we have seen in the past that we have called the systems where we cannot evaluate the internal forces using equilibrium equations alone, they are indeterminate system. Now, for such indeterminate system, if twisting moment acts, then what are the consequences, that we will be looking into this particular lesson. And finally, we will evaluate stresses and deformation in circular bursts due to torsion. Well, then the scope of this particular lesson includes, we will look into the aspects of the previous lesson as we will go through the answers of the questions. Then we will be evaluating the normal stress due to torsion and its consequences, then evaluation of stresses and deformation in indeterminate systems due to torsion, and then we will be looking into the examples for evaluation of stresses and deformations in bars of circular cross sections. Well, let us look into the answers of the questions which we had posed last time. Now, the first question posed was that if a bar made of a material which cannot withstand tension is subjected to torsion, then what will be the effect. Now, as you have seen that when we test a bar under axial pull, it undergoes extension, and the bar which can undergoes a large extension, we call those kind of material as the ductile material. Whereas, when we pull the bar, it does not elongate much, it because of the tensile stresses it breaks or it fails, we call those kind of material as brittle material. Now, if we use a material which is a brittle kind of a material, and if it is subjected to a torsion, and thereby there will be a tensile stresses, tensile normal stresses, then what is the consequence of that, that we will be looking into. So, let us look into that aspect of it. Now, if we have a bar which is subjected to a twisting moment of this form. Now, here this particular twisting moment is the positive moment as we had defined earlier. Now, because of this, see, this is the kind of stresses that will generate on the surface, which is the twisting moment which is in the form of a pure shear. Now, if we try to find out the value of the normal stress corresponding to that. Now, here because of this shearing stress, this is a positive shear. So, this is sigma positive axis, this is tau positive axis. So, if we plot that, since normal stress is 0, shearing stress value is over here, and for the complementary part we have normal stress 0, shearing stress over here. Now, if we plot the Mohr circle corresponding to this, then this is the value of the maximum normal stress which we call as sigma 1, and this sigma 1 is of magnitude equivalent to again the tau, this magnitude being tau, sigma 1 is also equals to tau. So, the maximum normal stress also is tau. Now, this particular point is at an angle of 90 degree from the reference plane which is this. So, in actual plane, so this is the Morse plane. Now, with reference to this, it is at an angle of 45 degree, where the direction of normal stress will occur, and perpendicular to this surface is the plane along which it is expected the failure to occur. Now, here if we look into that, this is the positive value which is occurring, and this is the plane 45 degree with respect to the x axis, and perpendicular to this plane is the failure line, and this is the plane along which it will fail. Now, if we take the bar in which if we have the torsion acting in this form, then again corresponding to this, if we plot the Mohr circle, we will have the sigma axis on this side, tau axis over here. Now, this direction of shear stress being negative, so you will have the point over here, the complementary point will come over here, and if we plot the Mohr circle again, the normal stress is going to be equals to sigma 1 here, and which is equals to tau. Now, this point will act in a clockwise direction with reference to the reference plane. So, this is the reference plane, normal to this is this particular line, and if we go 45 degree in the clockwise direction, then this is the direction of the normal stress sigma 1, and perpendicular to this is the failure line along which the failure occurs. Now, this can be demonstrated using a very simple experiment. Now, let us say that we take a piece of chalk which is a kind of a brittle material, and in fact, if we apply a twisting moment for the first case, which is in the anticlockwise direction, then you see that we get the failure is in this form as we have seen. This is the line which is inclined at an angle of 45 degree, and if you look into this particular line which is equals to the 45 degree as we have seen in the first case. Similarly, if we perform a similar kind of experiment, but this time we apply the twisting moment in a clockwise direction as we have seen in the second case, then you see the kind of failure which we have obtained, that is corresponding to the second case. So, this is a simple experiment to demonstrate that twisting moment when it acts into the bar, the failure line occurs along the perpendicular direction of the stress, or which is the failure plane. Well, let us look into this aspect a little more clearly, that this is the failure line along which, because of the twisting moment, along this bar is failing over here. Well, let us look into the second question then, that what is the relation between power and the torque. Now, having looked into that, because of the twisting moment, the tensile stresses which is getting generated on the surface, it causes failure which is perpendicular to the direction of the normal stress. Now, the second question is, what is the relation between the power and the torque when a shaft is subjected to a twisting moment. Now, in the last lesson we had looked into that power is generally defined as the rate at which work is done. Now, when we apply a twisting moment to a shaft, then the work done W may be defined as the torque, which is of constant magnitude, which is multiplied with the angle of rotation psi. So, power then can be written as P is equals to the time derivative of the work done, the rate at which the work is done. Now, W being T times psi. So, this is d dt of T psi. So, then T being constant, this is equals to T times d psi dt, and d psi dt is the angular speed which we have defined as omega. So, T times omega is equals to the power, where omega is defined in terms of the radians per second. Now, let us look into the some aspects which we had discussed last time about the units of it, that power which we generally write in terms of watt is equals to the twisting moment which is in Newton meter, and the omega, the angular speed, which is in radian per second. Now, frequency which we say the revolution per second, 1 revolution per second, and for 1 revolution as we have seen that it has to undergo 360 degree, which is equals to twice pi radian. So, we can write the angular speed omega is equals to twice pi f. Now, if we substitute for omega as we have seen p is equals to t times omega. So, for omega if we write twice pi f, then power is equals to 2 pi f t, where p is in watt, f is in cycles per second or revolution per second or in hertz. Now, sometimes frequency is used in terms of RPM, which is revolution per minute and designated by the term n. Then n by 60, this is revolution per minute, which is converted in second, is equals to f. So, n from this is equals to 60 times f. So, thereby the power P is equals to twice pi n t by 60, where t is in Newton meter again and n is RPM, the revolution per minute. Also, sometimes we define the power of the equipment from which the power is getting transmitted through the shaft in terms of the horsepower, which is in FPS unit. Now, so you should know the relationship between the horsepower and then the corresponding in SI units, which is in watt. So, 1 horsepower is equals to 746 watt approximately, and in foot pound again 550 foot pound per second. So, given the relation, given the values of the power in terms of horsepower or in watt, we can write down in terms of watt and then we can compute the values of the torque. So, these are the relationship between the power and the torque and then corresponding units which are being used for defining the power. Now, the last question which was posed was how will you evaluate stresses and deformation in circular bars for indeterminate system. Now, as we have discussed so long, we were looking into the systems of the bars where the bar is fixed it at one end and subjected to the twisting moment, or if you have a shaft which is fixed at one end, may be non-uniform, subjected to non-uniform torsion at different points. Now, in all these cases we could evaluate the values of the internal resisting twisting moment by employing the equations of equilibrium. If we could take the free body diagram and from that free body diagram we could able to evaluate the values of the internal resisting twisting moment. Now, if we go for a system in which the equilibrium equations alone are not adequate to evaluate this internal resisting twisting moment, then those systems are no longer a determinate system. So, if we come across such indeterminate system, then what will be the ways by which we can evaluate the internal resisting twisting moment. Now, one of such examples is supposing if you have a bar which is fixed at both ends and then if it is subjected to a twisting moment, then what will be the stresses in the bar or what will be the deformation in the bar which because of this twisting moment. If we like to evaluate that, this particular problem we cannot solve it by using equations of equilibrium alone. Now, for that we will have to, as we have seen in the past, that a bar which is an indeterminate one for evaluating the stresses and the strain, the axial stress and the strain, there we had to resort to the equations for the compatibility. Now, here also for indeterminate system we will have to generate additional equations from the equations of compatibility. So, once we have the equations of equilibrium and equations of compatibility, then we will be in a position to evaluate the internal resisting twisting moment, from which we can compute the value of stresses and the deformation. So, let us look into that how do we carry out that. Now, let us look into a system in which a bar or a shaft which is having different diameter. Let us say this diameter here is d 1 and this diameter here as d 2 and it is clamped at this particular end as well as it is clamped at this end. Now, if this is clamped and is subjected to a twisting moment, let us call this as a T 0, then what will be the values of the twisting moment at this end since it is clamped, and also what will be the stresses and the deformations in these particular zones. Now, as we can write down the reactive twisting moment like this. Now, this is the positive twisting moment, as we have defined that when it the twisting moment is an in anticlockwise direction, then the direction of the vector notation or the direction of the twisting moment is towards the thumb, and that is what has been shown over here. The twisting moment which is acting over here T 0 is the vector direction is this. So, this is T 0. Now, if that is acting in this particular shaft, then what are the reactive twisting moment at these two ends? They are in the opposite direction, which is in a clockwise form, and let us say that this point is A and this point is B, and accordingly let us call this as twisting moment at A and twisting moment at B. Now, obviously, then the twisting moment T 0 will be distributed in this reactive twisting moment, which is T A and T B. So, T 0 is equals to T A and T B. Now, this is the equation of equilibrium. Now, the external twisting moment which is acting in the shaft is getting equilibrated by the support twisting moment T A and T B. So, T 0 is equals to T A plus T B. So, this is the equation of equilibrium. Now, as you can see from this particular expression that T A and T B are the two unknown parameters, and we have only one equation. So, from one equation you cannot solve the two unknown parameters. So, you need an additional parameter to be brought in. Now, if you look into this particular one, now we consider a case as we have done in the past for indeterminate system, that this particular support we remove it, we remove this support from this particular shaft. Now, if we remove this particular support, then what happens? The consequence of this is that because of the twisting moment which is acting, the T 0, this will cause the rotation of the shaft, and let us say the rotation which it undergoes at this particular end, if we call this rotation as theta 1, which is at end B, is being caused by the twisting moment T 0. Now, let us remove this twisting moment and let us apply the resistive twisting moment, which is T B at this end, and this T B also is going to cause a twisting moment over here. Let us call this as theta 2. Now, this particular support B being fixed in position. So, it is expected that there will not be any rotation because of the twisting moment. So, the net rotation at support B is equals to 0. So, the theta 1 which we get corresponding to the twisting moment T 0 and theta 2 which we get corresponding to the resistive twisting moment T B, that should be equals to 0. So, if we substitute that means, if we write theta 1 plus theta 2 equals to 0, and then theta if we write in terms of a twisting moment T, then we get another set of equations. So, we get equation 2 and this is equation 1. So, from these two equations we have two equations now, and we have two unknown parameter T and T B, then we can solve for T A and T B. So, an additional equation has been generated from the deformation compatibility in this particular case, and we call this as a compatibility equation. So, for indeterminate system, in fact, we need the equations of equilibrium to be written, we need equation of compatibility to be written, which is as a function of the twisting moment, which is as a function of the rotation theta, and then we write the torque displacement relation. So, that we can get this compatibility equation in terms of twisting moment T. Then we have two equations from which we can compute the unknown values T A and T B. Now, let us look into another kind of a system in which if we apply a twisting moment. Now, let us say that we have a solid bar, this is the solid bar of diameter d 1 is inserted within a tube. This is a tube, let us call this as 1 and this tube as 2. Now, this is the tube, this is the one side cell, this is the other side, which is a circular one. Now, a circular tube is there within which we have a solid shaft inserted in. On one end it is clamped, the other end we have put a plate which is connected to both the tube and the solid shaft. Now, if the whole assembly is subjected to a twisting moment, then what is the consequences? Now, since both the ends are fixed naturally and you have two elements, one is the tubular shaft, another one is a solid shaft, and both the elements are subjected to a twisting moment in a combined form. Now, if we like to find out that what is the share of this twisting moment between the two elements, the tubular shaft and the solid shaft, there are two twisting moments that will be shared by these two elements, then how do we evaluate those twisting moments? Now, let us look into this. Now, supposing if we take off this particular plate, rigid plate from this and take out the shaft over here. So, this is the solid shaft, internal solid shaft, which is subjected to a twisting moment, vectorial notation of which is this, and let us call that twisting moment as T 1. That means, the external twisting moment T, which is acting in the composite system, is shared by the shaft and the tube. Now, the twisting moment which is acting in the solid shaft, central solid shaft, is equals to T 1. The twisting moment which is acting in the tubular form is equals to T 2. So, we have T 1 and T 2, and the diameter of the internal shaft is equals to D 1 and the external diameter or the outer diameter of the tubular shaft is D 2. Now, we will have to find out the values of T 1 and T 2. Now, if we write down the equilibrium equation, then external twisting moment T is equals to the twisting moment T 1 plus T 2, because this external twisting moment T is to be shared by the solid shaft and the tubular shaft. Now, again we have only one equilibrium equation and we have two unknown parameters T 1 and T 2. So, from this single equation we cannot evaluate the values of T 1 and T 2. So, we need an additional equation to be generated, so that we can evaluate these two unknown values T 1 and T 2, and this additional equation can be generated if we take the compatibility into account. And what is the compatibility criteria in this particular case? Here you have the composite system where you have external tube in which you have a solid shaft and both are enclosed within two fixed supports. Now, when this is being twisted, now the whole composite system is undergoing a rotation, and also since both the tube and the solid shaft are under the constraint of these two plates, they are expected to undergo the same amount of rotation. So, the rotation in the solid shaft and the rotation in the tubular shaft, they should be identical, and that is the compatibility from which we can generate additional equation. So, now if we say that this is the rotation theta 1 that this particular solid shaft is undergoing because of the twisting moment T 1, and if we say theta 2 is the twisting moment, I mean the rotation that is being that this tubular shaft is undergoing because of the twisting moment T 2, then we say that theta 1 is equals to theta 2, and this is compatibility equation. So, this is our equilibrium equation where we say that T is equals to T 1 plus T 2, and this is our compatibility where theta 1 is equals to theta 2. Now, theta 1 and theta 2, now if we write in terms of the twisting moment, as we know that T by j is equals to tau by rho is equals to g theta by L. So, theta in terms of T is nothing but is equals to T L by g j. So, the value of theta in terms of T is equals to T L by g j. So, if we write down that theta 1 is equals to T 1 L being the same, because both are within the same confinement. So, the length of the solid shaft and length of the tube are identical, and let us call that as L. So, T 1 L by g, and let us call this as J 1, which is the polar moment of inertia of the solid shaft. Likewise, theta 2 will be equals to T 2 L by g j. Now, if we have the same material or J 2, if both the tube and the solid shaft made out of the same material, then the shear modulus value G will be identical. But if this tube and the solid shaft they are of different material, then you will have two different values of G, and correspondingly we will use G 1 and G 2 to make it more general. So, now that if we equate this theta 1 and theta 2, we can get a relationship between T 1 and T 2. So, that is the second equation which will be generated from this compatibility. So, equation 1 and equation 2 can give us the values of T 1 and T 2. So, these are the two equations T 1 T equals to T 1 plus T 2 and theta 1 equals to theta 2 or T 1 L G J 1 is equals to T 2 L G J 2 will give us the values of T 1 and T 2. So, that is how for an indeterminate system, when they are subjected to a twisting moment, we make use of equation of equilibrium, equation of compatibility and then the torque displacement relationship to arrive at that what will be the equations from which we can evaluate the unknown twisting moment or the internal resisting moment. And once we know these twisting moments, then we can take the free body diagram of the whole shaft at any point and then correspondingly we can find out what are the internal resisting twisting moment and from which we can compute the value of the shear stresses which are generated from the twisting moment and the angle of twist because of this twisting moment. Well, then if we look into the whole of this which we have done so long for the determinate and indeterminate system. Now, torsion of circular shaft, when we talk about the determinate system, the equations which we need are the equilibrium equations and mind that equilibrium equations alone are adequate to evaluate the internal resisting twisting moment and all we need is a torque displacement relation or torque rotation relationship from which we can compute the value of the stresses. Now, also the geometry of deformation as we have seen, which is in terms of the rotation, it varies and shear strain varies linearly from the axis of the shaft, that we have seen that gamma is equals to d theta dx times rho. So, it varies linearly with respect to the radius from the center as it goes, it varies linearly and shear strains are related to the shear stress which is the constitutive relationship. So, with these three aspects we can solve any determinate system. Now, in case of indeterminate system, they are also identical except that, so you need equations of equilibrium, you need to look into the geometry of deformation and of course, the shear strain is related to the shear stress which is the constitutive relationship. Now, apart from this, these alone are not adequate to give the equations for evaluating the internal resisting twisting moment. Now, in case of indeterminate system, we need another criteria which is the equation of compatibility and from this equation of compatibility we can generate another equation and from which we can solve the internal resisting twisting moment and thereby internal twisting moment at any point in the shaft in terms of those support moments. So, now that you are in a position to distinguish that if a bar which is supported at one end and subjected to a twisting moment, then we can compute twisting moment at any point, whether it is uniform torsion or non-uniform torsion or whether the shaft is uniform or non-uniform and accordingly we can compute the value of the twisting moment and I mean the stresses and then corresponding the angle of rotation. Now, if the bar is not supported on one point alone, it is supported at 2 points or 2 sides, then it is when it is subjected to a twisting moment, then equations of equilibrium alone is not adequate to evaluate the internal resisting twisting moment and we need the support of equation of equilibrium to generate additional equation from which we can compute the values of internal resisting twisting moment. So, now let us look into some of the examples to demonstrate this. Well, now the first example is the one which of course, I had posed last time and I am sure you have done, and this aspect we discussed last time that the shafts are generally used to transmit power, and in this particular case a tubular shaft is designed to transmit 120 kilowatt power at a frequency of 15 hertz. Now, the inside diameter of the shaft is to be 3/4 of the outside diameter. So, if outside diameter is d, then the inside diameter is 3/4 of d, which is 0.75 times d. Now, if the allowable shear stress is the 45 MPa, then what is the minimum required diameter d? What will be the minimum required outside diameter d? So, let us look into this particular example, that how do you solve it. Now, here the value of power given as equals to 120 kilowatt and the frequency at which the shaft is operating is 15 hertz. So, as we have seen that P is equals to twice pi f t, that is the relationship between the power and the torque. Now, power here of course is in watt. So, since it is given in kilowatt, so this is 120 into 10 to the power 3, this is equals to twice pi, f is 15 and t is the twisting moment which is in Newton meter. So, t then is equals to 120 into 10 to the power 3 divided by 30 pi, and this gives us a value of 1273.24, so much of Newton meter. So, this is the value of the twisting moment that is being generated because of the power driven, which is 120 kilowatt at a frequency of 15 hertz. Now, given that the outer diameter of the shaft d outer is equals to d, and consequently d inner is 3/4 of the outer diameter, which is 0.75 times d. So, if these are the values of the shaft, the d and 0.75 d, then the value of the polar moment of inertia j is equals to pi by 32 d outer to the power 4 minus d inner to the power 4. So, this is equals to pi by 32. Now, d outer here is d. So, d to the power 4 minus 0.75 d to the power 4. Now, this gives us a value of 0.684 pi. So, this is equals to 0.684 pi by 32 times d to the power 4. So, this is the value of j. This is the value of the polar moment of inertia j. Now, as we know that the stress is limited to 45 MPa. So, T by j is equals to tau by rho. Now, we will have to find out the diameter d. So, here T is 1273.24, so much of Newton meter into 10 to the power 3, so much of Newton millimeter divided by 0.684, that is what we have computed, times pi times d 4 divided by 32. So, this gets multiplied by 32. So, this is equals to tau is limited to 45 MPa and rho is outer diameter by 2. So, 2 divided by d. So, from this if you compute the value of d, d comes as 59.51 millimeter. So, this is the diameter of the shaft that we will have to use, so that the stress is within 45 MPa. So, if we have to use a shaft, a tubular shaft which is transmitting power at 120 kilowatt and at 15 hertz frequency, then the diameter of the external diameter of the shaft that is necessary is equals to 59.51 millimeter, if we have to restrict the value of the stress, the shearing stress within 45 MPa. So, if we use the diameter more than that, then the stress level will be lower, but if we go diameter lower than this value, then the stress level will go higher and as a result the shaft will fail. Well, let us look into this second example, which is of the category which we have discussed today, which is an indeterminate system. Now, you have a shaft A, B and C, with solid circular section. Now, the diameter of this part, it has a 2 part which is a stepped one, and the first part is having a diameter of 16 millimeter, the second one is having a diameter of 20 millimeter, and it is held against rotation at A and at C. If the allowable shear stress in the shaft is 60 MPa, so tau is limited to 60 MPa, then what is the maximum torque that may be applied at B? So, the torque T which can be applied at B, maximum torque at B, so that the shear stress does not go beyond 60 MPa. Now, here since these two ends are clamped, so here resisting twisting moment will be T A and T C, and obviously from the equilibrium equation we know that T A equals to T A plus T C. Now, T A and T C being two unknown parameters from single equation, we cannot evaluate that. So, it is a problem of again the indeterminate system. Now, let us look into this free body diagram. If we take the free body of the shaft, now here we have the twisting moment that we will have to evaluate is T, which is acting at B, and the resistive twisting moment at end A and AC, if we say T A and T C, then our equilibrium equation gives us that T is equals to T A plus T C. Now, please note here that this twisting moment which is acting here is a positive twisting moment. This is the vectorial notation of the twisting moment, and the support twisting moment which we have taken is in the opposite direction, T A and T C, and this is the equilibrium equation, T is equals to T A plus T C. Now, so this is equation 1. Now, another equation we can generate from the compatibility criteria. Now, when this is subjected to a twisting moment here at T, and mind that this is acting at this point at B. Now, once we have removed this particular support, it becomes a determinate system. Now, if we cut across here and take the right hand free body, then since here there is no twisting moment, so from part B to C it is free of twisting moment, but between A and B we have the twisting moment T. Now, if we try to find out the rotation here, which let us call this as theta 1, which will be occurring because of the twisting moment T at C, and in this particular free end at C, because of the resistive twisting moment T C, there will be another rotation, and let us call this rotation as theta 2. So, what is going to happen is that this theta 1 and this theta 2, if we combine together, since this end is fixed, it cannot undergo any rotation. So, theta 1 plus theta 2 should be equals to 0. So, this is the equation of compatibility, and then this if we write theta 1 and theta 2, if we write now from theta 1, from this particular free body diagram, theta 1 is going to be equals to T when it is subjected to the action of T over the length A B. So, T L A B by G J A B, that is the polar moment of inertia of the part A B. Now, since there are two different diameters, so J A B and J B C are different. Now, when this particular shaft is subjected to a twisting moment at C and undergoing a rotation of theta 2, now the value of theta 2 will be equals to the twisting moment T C. Now, for part A B it will be length A B by G times J A B. Also for the part B C there will be a rotation. So, there will be plus T C times length B C divided by G J B C, and if you note here that the twisting moment T is acting in the positive direction, as we have defined earlier that when it moves in an anticlockwise direction. So, the direction of the twisting moment is in the positive x direction. So, the rotation correspondingly also is positive, and T C is acting in the opposite direction, which is a negative. So, theta 2 as a whole is a negative. So, theta 1 plus theta 2 equals to 0 will lead theta 1 equals to theta 2, and from this we can find out the relationship between T C and T, and we have already a relationship between T A and T C. So, from this we can evaluate T A and T C. Now, let us compute these values. Now, as we have seen, T is equals to T A plus T C. This is our equation of equilibrium. This is equilibrium equation. Now, equation of compatibility. equation of compatibility gives that theta 1 plus theta 2 equals to 0. So, this is the second equation. Now, we will have to apply the torque rotation relationship, which is theta 1 is equals to T A times, or let us call this as theta 1, which is arising because of the T, let us call this as T times length A B divided by G J A B, which we have seen just now that the rotation theta 1 is occurring because of twisting moment T, which is over length A B times G J A B, and theta 2 correspondingly is equals to, which is corresponding to T C times length A B divided by G J A B plus T C length B C by G J B C. So, this is the total twisting moment, which is negative according to the sign convention which we have used. Now, if we write down this theta 1 plus theta 2 equals to 0 as our equation of compatibility, then we have T L A B by G J A B. This is equals to T C L A B by G J A B plus T C L B C by G J B C. So, this is the second equation after writing the relationship between the angle of twist and the twisting moment, and we have equation of equilibrium, which is T equals to T A plus T C. So, if we now substitute the numerical values, then which we have that T length A B is 125 by G gets cancelled from either side. Now, before we go into this, let us compute the value of the polar moment of inertia J for the two part. Now, J for A B, which is of diameter 16, is equals to pi by 32 times 16 to the power 4, which is equals to 6434 millimeter to the power 4, and J B C is equals to pi by 32 times this is 20. So, 20 to the power 4, this is equals to 15708 millimeter to the power 4. Now, if we substitute now that T times length A B is 125 by J of A B, which is 6434, this is equals to T C length A B is 125 by 6434 plus we have T C into 250 divided by 15708, and this comes that T into 0.0194 is equals to T C times 0.0353, and this gives a value of T C as equals to 0.55 T. So, once we know these, from equation 1 we get T A as equals to 0.45 T. So, now that we know the values of T A and T C in terms of T. Now, if we have to restrict the value of stress to a value, or we need to evaluate the values of the twisting moment, what will be the value of the twisting moment T if we restrict the stress tau to 60 MPa. The stress is to be limited to 60 MPa, and correspondingly we will have to find out the value of tau. Now, if we take the value of tau as now T by J is equals to tau by rho, this we know. So, we say the tau is equals to T rho by J, and tau for AB part let us say is restricted to 60 is equals to T A times 8 is the rho because 16 is the diameter divided by J A B which is 6434. Since we are using the twisting moment T A over the part A B, then twisting moment which is acting at T A, if we take a section in between A B, then the resistive moment also will be T A. So, over the part A B if we compute the stress which is equals to T times rho by J. So, T rho is 8 and J is 6434. From this the value of T A comes as equals to and T A is as we have seen is equals to 0.45 times T. So, if we substitute that, this gives us a value of 107.3328 or 23. So much of MPa. Now, this is the value of the twisting moment from the part A B. Now, let us see the value of the twisting moment from the part B C. Now, from the part B C again we can say tau is the shear stress which is limited to 60 MPa is equals to T B rho B C by or T C rho B C by J B C. Now, T C is equals to 0.55 times T, rho B C is equals to 10 and J B C is equals to 15708. And from this and tau as we are limiting it to 60 MPa. So, from this if we compute the T comes as equals to 171.4 Newton meter. Now, out of these two values of twisting moment, now here if we have this is not T A, this is T because T A is 0.45 times T. Now, from this we compute we get T which is 107.23 MPa and from here we compute T which is 171.4 Newton meter. Now, if 171.4 Newton meter acts at B, then the stress in the part A B will go beyond 60 MPa and the shaft will fail. So, we will have to restrict the value of the twisting moment at B as 107 Newton meter. So, that the stress level everywhere is within 60 MPa. Well, we have another problem which is again of similar type, that means of indeterminate system. Now, we have a solid steel bar of diameter 30 millimeter is enclosed by a steel tube of outer diameter 45 millimeter and inner diameter 36 millimeter. Here we have a solid shaft of 30 millimeter diameter which is inserted within a tube. This is the tube of outer diameter 45 millimeter and inner diameter 36 millimeter. Now, both bar and tube are held rigidly at end A and B. This is the end A and this is the end B. They are held rigidly by the plate and joined as a rigid plate at B. Now, you will have to determine the maximum shear stresses in the bar and the tube. Now, because of this we will have to find out how much shear stresses are generated in the bar and the tube, and also you will have to determine the angle of rotation of the end plate. Now, the value of G is given as 80 MPa. Now, let us look into the free body diagram of this particular system. Now, here as you can see that this is the solid bar or the solid shaft and this is the tube, and this solid shaft is inserted within the tube held at this end A, and also we have provided a plate, rigid plate at B. So, this is held between the two ends and it is subjected to a twisting moment. The whole composite system is subjected to a twisting moment which is of magnitude 500 Newton meter. Now, the diameter of the solid shaft is 30 millimeter, the diameter of the tubular part, the external diameter is 45 and the internal diameter is 36 millimeter. Now, let us call that this is subjected to a twisting moment T 1 and this is subjected to a twisting moment T 2. So, the equilibrium equation will tell us that the T which is equals to 500 Newton meter is equals to T 1 plus T 2. So, this is the equation of equilibrium, and also because of this twisting moment T 1, this will have a rotation theta 1, and because of this twisting moment T 2, it will have a rotation theta 2. Now, since they are enclosed, the whole assembly is enclosed between two plates. So, the rotation theta 1 and theta 2 they should be identical, because you cannot have dissimilar rotation for the two different parts when they are attached between the two plates. So, theta 1 should be equals to theta 2, and that is the compatibility. So, theta 1 is equals to theta 2, and theta 1 in terms of T 1 we can write as T 1 L by G J 1, and this is equals to T 2 L by G J 2. This material being the same, the G value will be the same, and J 1 J 2 are the polar moment of inertia of the shaft and the tube. So, from these two expression we can evaluate the value of T 1 and T 2 and thereby the stresses. So, now let us compute that if we write down, then the equilibrium equation 500 is into 10 to the power 3 so much of Newton millimeter is equals to T 1 plus T 2. So, this is equation 1, and second equation is theta 1 is equals to theta 2. This is the second equation, and from first theta 1 we can write that T 1 times L by G J 1 is equals to T 2 times L by G J 2. Now, here since G is the same, so G gets cancelled, L also is the same, it gets cancelled. So, T 1 is equals to J 1 by J 2 times T 2. Now, J 1 for the solid shaft is equals to pi by 32 times the outer diameter is 30. So, 30 to the power 4, and this gives us a value of 79521.6, so much of millimeter to the power 4, and J 2 is equals to pi by 32 times we have 45 as the outer diameter minus 36 as inner diameter, and this gives us a value of 237682, so much of millimeter to the power 4. So, this is the value of J 1 and J 2, and consequently, if we substitute here we get T 1 as equals to 0.335 times T 2. So, we have T 1 plus T 2 as equals to 500 into 10 to the power 3. We have the value of T 1 as equals to 0.335 T 2. So, if we substitute by the equation 1, we get the value of T 2 as equals to 374.532, so much of Newton meter, and T 1 we get as 125.468, so much of Newton meter. Okay, so, these are the values of T 1 and T 2, and correspondingly then the shear stress tau 1 is equals to T 1 rho by J 1, and if we substitute the values it will come as 23.7 MPa. Tau 2 again as T 2 rho by J 2, and if we substitute the values this will come as 35.5 MPa. So, this is the values of the shearing stresses for the two elements. Now, theta, since they are same, we can, if we compute for theta 1, which is T 1 L by G J 1, this is equals to if we substitute that 125.468 into 10 to the power 3 into L is 500 divided by G is 80 gigapascal, so much of megapascal, times 79521.6. If we substitute that, you get a value of 0.00986, so much of radian, and if we multiply by 180 by pi, then you get so much of degree, which is 0.565 degree. So, this is the amount of rotation that you have. Now, theta 1 if we compute, theta 2 also is automatically computed, because theta 1 is equals to theta 2, and that is the rotation for the whole assembly. Now, if we like to compute the stiffness of the whole composite system, as we know that T is equals to G L by J times theta. So, G J by L, that means rotation per unit length is our stiffness. So, G J by L can be computed as T by theta. So, we know theta, we know T, we know how much is the torsional stiffness of the whole composite system. Okay. Then to summarize now, for this particular lesson we have evaluated the maximum normal stress due to torsion in the shaft, and we have seen that how the failure line occurs because of this maximum normal stress. The direction of the normal stress, if we compute the perpendicular direction to the normal stress direction, is the one which is the failure line, and that is at 45 degree, which we can see from the Mohr circle event. Then we have seen the evaluation of stresses and deformation in indeterminate system due to torsion, and then we have seen some examples to evaluate stresses and deformation in bars of circular cross section due to torsion. So, in this particular lesson we have dealt with the indeterminate system, and we have seen that how now internal resisting twisting moment can be evaluated in case of indeterminate system. In case of determinate system, we had computed directly from the equations of equilibrium. Now, for indeterminate system, apart from the equations of equilibrium, you need the equation of compatibility as well, and then you can evaluate the values of the internal resisting twisting moment, and you can compute the value of the stresses. So, in fact, this is the last lesson on the module on torsion. We had 4 lessons in this particular module, which is on torsion. It had 4 lessons, and the first lesson, in the first lesson we had discussed the effect of torsion on solid circular sections, and then we had seen that how to compute the stresses and the angle of rotation because of the twisting moment when it is acting in a solid circular shaft. Consequently, in lesson 2 we had looked into that how to compute the values of the stresses and the angle of rotation if the twisting moment acts in a hollow shaft, if the shaft instead of a solid circular one, if it is a hollow one, and that is what we had seen in the lesson 4.2. In the third lesson, which is L 4.3, we had seen the aspects of the power transmission through these shafts, and we had seen the relationship between the power and the torque, and then from which we could compute that what could be the stresses and the angle of rotation in the shaft when that particular shaft is being utilized for transmitting power from one device to the other. And then lastly, the fourth lesson, which was this particular lesson, in which we have discussed the aspect of the evaluation of internal resisting twisting moment for indeterminate system, and consequently what are the stresses and the deformation that occurs because of the twisting moment. Well, we have some questions set for you, which is based on the discussions which we have on this module, which is how the strength to weight ratio. Now, strength to weight ratio is a term which we have evaluated. In fact, if you go through the lessons, you will know that how the strength to weight ratio of a bar subjected to torsion is defined. Now, what is the torsion equation, and what is the value of maximum normal stress in a solid circular shaft which is subjected to a twisting moment T. Now, this is the maximum normal stress which is subjected to a twisting moment that we have discussed, and so you should be in a position to answer these questions. We will give the answers for this question in the next lesson. Thank you.